Okay, this is topic 4.1. It's properties of materials, and this is quite a long section and quite a big topic, so we'll break it into a couple of different lectures. But let's start with this, that when we're talking about properties of materials, we're looking at the physical properties, the mechanical properties, the aesthetic characteristics, and we'll also be looking at some smart materials. So here we go. Let's start with some physical properties. So the first physical property we want to look at is density. And so density is mass per unit volume of a material. It's really important when we're talking about weight and size. And basically what it is, density is a ratio between the mass of something and its volume. And usually it's measured in a couple of ways. You either measure it in grams per cubic centimeter. So you would be looking at, okay, how many grams, these are cubic centimeters right here, how many grams of copper are in a cubic centimeter of copper. So this is going to be, of course, more than, say, the number of grams that are in a cubic centimeter of plastic. This is lead down here. Lead is going to have more grams, so it is more dense in this cubic centimeter than, say, copper or plastic. You also often find it as in kilograms per cubic meter, so that's sort of an industrial one, so you might see it there as kilograms per cubic meter. Okay, but density is very, very important. Some context that you might want to pay attention to is like packaging for food. Instant noodles are sold by weight and volume. Packaging foams, things like that, will have low density, which will allow you to save on things like the weight of an object. All right, electrical resistivity. So here is a measure of the ability of a material to conduct electricity, and the material with low resistivity will conduct electricity well. So if it does not resist, so resist means to stop. If it does not resist electrical energy, then it's going to have a low resistivity. So the best electrical conductors are actually silver. Silver's the best, and then gold, copper, steel, seawater. Actually, I think aluminum should be right there. But these are all examples of electrical conductors. Silver's the best, but unfortunately silver tarnishes. But for instance, in computers, you often find that really sensitive connections in computers are made out of gold because it does not tarnish or oxidize. Here's some things that have a high degree of electrical resistivity. So something like rubber, glass, oil, diamond, wood. So these things are going to resist the flow of electricity through them. This is also why you find, for instance, rubber or plastic around a electrical cable so that the electricity can flow through the metals inside. It's usually copper inside a cable. So, for instance, this black part right here is going to have high resistivity, and this is going to have low resistivity. That allows you to touch it without electrocuting yourselves. So that brings us to insulators and conductors. So an insulator reduces transmission of electrical charge, and again, this is this is insulation right here, this white and black stuff, and then also the blue and white and the yellow and any of the plastic that's around these will stop. It'll reduce the transmission of an electrical charge, and then a conductor will allow the transmission of an electrical charge. Thermal conductivity is actually quite similar to electrical, and you do find actually that for instance, silver is the best conductor of heat also. So when we're talking thermal, anytime you see therm, remember that has something to do with heat. So this is a measure of how fast heat is conducted through a slab of material at a given temperature with a given temperature difference across. So this is a definition you should know, across a slab. But essentially, it's like how well does a material allow heat to conduct. So for instance, often you'll see that things like these conducting rods will allow you to do some measurements on that. Notice that the handles of all of these rods are made out of wood because wood has a low thermal conductivity. It does not conduct heat very well. So a metal usually does. Metals have free electrons, and that allows them to conduct electricity much better than something like wood, which does not have free electrons. And that also goes with electricity. So because metal has free electrons, it will allow electricity to be conducted, and so same with heat. Okay, so these metals tend to be better conductors of heat, and non-metals tend to be worse conductors of heat. Okay, thermal expansion. So thermal expansion is the measure of the degree of increase in dimensions when an object is heated. So essentially, because you're heating an object, the molecules and atoms within that within that object are moving faster and faster and faster, and they take up more space and they expand. So when you heat something, they expand, and when you cool something, it contracts. Okay, now this is there is one glaring exception to that, which is actually water. Water will contract as you cool it to a certain point. I believe it's around 5 degrees Celsius, and then it will start to expand as it becomes a crystal. But most things contract as they are cooled and expand as they are heated. And now this is important because, for instance, in things like bridges, what you do is you put in thermal expansion joints within the bridge itself, so that as the bridge expands or contracts, it has room to do that. So these teeth right here will push closer together as the bridge expands, and they will pull further apart as the bridge contracts in cold weather. And this is very important. If you didn't have those, then the bridge would buckle and fail. You also see these in sidewalks, so the cracks in sidewalks also are for thermal expansion. Okay, so that's so thermal expansion is that measure of how much will something expand, and of course, different materials will expand with a different amount depending on the properties of those materials. But it is definitely something you want to pay attention to when you are designing, because if you're designing something that is going to need to be in an environment where there's a lot of change in temperature and it's prone to lots of thermal expansion, then you're going to want to design in something that will allow you to allow that thermal expansion and contraction. Okay, hardness. So hardness is the resistance of a material to penetration or scratching. Okay, and this is just a quick one of the hardness scales that we use for rocks and minerals. So this is on a 10-point scale. It's called the Mohs hardness scale, and you can see that at the very top, at number 10 is a diamond. So diamond is very resistant to scratching. Okay, it would be very difficult for you to scratch a diamond. The only thing that really scratches the diamond is another diamond. Now, talc, which is a very soft mineral, is very easy to scratch. You can scratch it with your fingernail, and same with gypsum. Okay, you can use a knife or a glass plate, and you can scratch anything like apatite. So anything with a higher number will scratch a lower number. So for instance, orthoclase will scratch apatite, and apatite will scratch fluorite, but fluorite will not scratch apatite. So anything with a higher number will scratch a lower number, and anything with a lower number will not scratch a higher number. Now, be careful. Hardness does not equate to toughness, and we'll talk about toughness in a couple of minutes here. But toughness is something that is different than hardness. Okay, so some mechanical properties. Mechanical properties, we have something called tensile strength, and this is the ability of a material to withstand pulling forces. So when you have something that is pulling on either side of a material, how resistant is that material to those pulling forces? And that's the tensile strength of an object. This is really important when you are having, especially when something is hanging. Like for instance, a bridge that's hanging from cables, you need to have material that is very resistant to tensile force, or very strong, that has very strong tensile strength. Okay, so that's a mechanical property we need to pay attention to. We also have compression. So compression is the ability of a material to withstand being crushed or squashed. So, the more resistant you are to being squashed, the more compressional strength you have. We have elastic materials which will bend when they're squished and then should reform. There's a whole YouTube channel devoted to hydraulic presses crushing different things, and so if you look at that, you can kind of get a sense of what different materials react like under compressional force. A rigid material like this brick will shatter under these kinds of compressional forces. So this is definitely something that we need to pay attention to whenever we have something that is kind of being squished. So for instance, if you're building a house, you want to pay attention to this because the force of, like for instance, let's say you're using bricks, the force of the bricks on the bottom, the forces that are acting on the bricks on the bottom of a wall is much greater than the force on the top. So it's important to make sure that you have something that can resist compressional forces on the bottom of things like walls. Otherwise, they will easily smash or break, and then the whole wall will come down. Okay, stiffness. So stiffness is the resistance of an elastic body to deflection by an applied force. So this is where if you think of something that you can bend so far, and then it'll start to it won't snap back. Okay, so when we're talking about this is stress and this is strain. So when we're looking at this, we're looking at where is the point where something will actually bend and not go back to its original shape, and that's stiffness. Okay, and again, we need to design for this. We need to think about where do we want things that are stiffer and where do we want things that are more flexible. Okay, so that's something to definitely pay attention to when an elastic body is deflected and comes back. All right, toughness. So toughness is the ability of a material to resist the propagation of cracks. Now, I do want you to be a little bit careful of this because some objects are hard but not tough. Like glass is hard. Glass is quite hard, but it is very brittle and it's not very tough. These are called material selection charts, and we'll talk more about them later. But basically, you can see that the things that are toughest are over here. Okay, so at the top right-hand corner of this graph, you're getting things that are toughest. So they're both strong, they can resist a lot of pressure, and they're tough in the sense that they won't allow cracks to form. So for instance, a hammer, you want it to be tough. You want it to be something that you can hit and not shatter, right? Glass, well, glass is great for a lot of things. Glass is quite strong, quite strong. Like it can resist a lot of pressure, but it is quite weak and brittle when you're talking. It's quite brittle, when you're talking about its toughness. So just try to remember, toughness and hardness are two very different things. This hammer right here is very tough, but it is not very hard. You could take a diamond and scratch this hammer, put some big scratches in this hammer, but you could then take this hammer and hit the diamond with it, and it would shatter into a million pieces. Okay. Let's talk about ductibility. So ductibility is the ability of a material to be drawn or extruded into a wire or some other extended shape. This is a video you can kind of get a sense of what ductibility looks like. This is aluminum extrusion. So some materials are better at being drawn into wires. This is particularly things like metals. Metals can be drawn into wires or other extended shapes. But something like, again, I'm going to come back to diamond. Diamond, not very good at being drawn into an extended shape. So it's going to have a low ductibility, whereas something like aluminum has a relatively high ductibility. Okay, we get to aesthetics. So aesthetics are an aspect of a product that relates to taste, texture, smell, and appearance. It's basically, does something look nice, smell nice, feel nice, taste nice, right? So that's an aesthetic quality. So some aesthetic character, this is from the IB, and so just take this with a grain of salt here. Some aesthetic characteristics are only relevant for food, while others can be applied to more than one material group. Although these properties activate people's senses, responses to them vary from one individual to another, and they are difficult to quantify scientifically, unlike other properties. So this is aesthetic characteristics. What they're saying is they're kind of difficult to get a measure on because it's all about individual taste. So you would be using things like Likert scales, ratio scales and things like that to measure how people feel about aesthetics. But aesthetics is essentially, does it look nice? Now, what looks nice to me may not look nice to somebody else. Like, for instance, some people just really love ornate furniture like this. Like, they find this very appealing. They would love their living room to look like this. Whereas I'm a little more, my aesthetics go a little more like this, where you're, it's a little more plain, simple, modern, not a lot of stuff everywhere, just, kind of clean surfaces. That's an aesthetic, and it's very dependent on culture. It's dependent on the time period and fashion and you name it. So there's a lot of aspects that go into your aesthetic. So it's something to pay attention to as we're designing. What kinds of aesthetics do people like? Okay, now we're getting into something called smart materials. So smart materials are materials that are, like, for instance, well, they're just kind of cool. They have lots of different features, and this is an example of something called piezoelectricity. So a piezoelectric material gives off a small electrical discharge when deformed. So this video will explain a little bit about piezoelectric materials, so please do watch this, and you'll get a good idea of what piezoelectricity is all about. Okay, nitinol is another interesting material, and it's a shape memory alloy. So it remembers its shape, and it can spring back to that shape once it's been released. And this is a really cool video. It shows you some interesting stuff about nitinol. So please do have a look at that, and it's a shape memory alloy. Okay, photochromacity. So a photochromatic material changes color in response to an increase in light. So now this is important. It's actually not changing color so much. It's actually reducing the amount of light that can come through it. Okay? So be careful about this whole color thing. It doesn't really change color. It more or less adds sort of a shade to it. So this is the definition that we have in our glossary of terms, but I would try not to use color. I would try to think of this as more or less a something that it's basically adding, it's blocking, it's creating shade within there. So literally, I mean, this video will show you how it works, but literally what happens is the molecules reform themselves and stop some of the light from coming through. Okay, we have something called electrorhestatic or magnetorostatic. This smart material relates to a fluid that can undergo a dramatic change in viscosity. So viscosity is the measure of how easily something flows, right? So water has a certain viscosity, but if you think of maple syrup flows slower, or honey flows slower than water. It flows, so we would say that honey and maple syrups are more viscous. Okay, so when you expose these materials to electrical or magnetic fields, they become more or less viscous. And that's important, and this is an example of that. So go ahead and watch this video, and it'll show you an example of electro and magneto rheostatic. Okay, we have thermoelectricity. This refers to a smart material where heat can be produced. It can produce an electrical charge. Thermoelectric material is composed of dissimilar conductors, and I'm not sure why this video, I'll have to check on this, but I'm not sure why that video is not working. But actually, this girl spoke at our school, this woman spoke at our school a few years ago. She invented a flashlight that just uses the heat from your hand in order to make it light. Okay, so that's thermoelectricity. Okay, we have elastic materials. So this is materials that can return to their original shape after being deformed. So that's for instance, you can see lots of different examples here: spring steel, foam, rubber. These are all examples of things that can return to their original shape after being deformed. Plasticity. So plasticity is the ability of a material to be changed in shape permanently. So it's different than elasticity. So for instance, this is plasticity. This paperclip was bent and it's now in a new shape and it's not going to return to its original shape. That would be elasticity. You can bend it back into its original shape. It does have some elasticity, but it's more plastic than elastic, or its elasticity ends at a certain point and its plasticity picks up. And we'll talk about that when we get into some of the charts and graphs in the next section. All right, and I'm going to stop there. We'll pick up this lecture in the next section. Thanks for watching.